This video will demonstrate the measurement of a small 5 GHz patch antenna using the DAMS Model 5000 positioner and FSM5 full spherical mount. We'll be using a 1 to 18 GHz broadband reference antenna as a source, and the path separation is 1 meter. The VNA is an HP8722 configured in S21 mode.
You are now looking at the front page of the DAMS Antenna Measurement Studio software. In the upper left is where you select what type of test equipment you will be using. In this case, we have an HP8753 selected, which also controls the HP8722. You can see from the list that we support a wide variety of devices. This is just the source or VNA list. Receivers such as power meters and spectrum analyzers can be selected from this list below. The software can also function in a receive-only mode, so you can measure self-generating devices. Here you will see you can select the extents of your measurement, such as the start and stop position and resolution. Right now it is configured for 0 to 360 degrees in 5 degrees per measurement. The elevation extents are also shown as -90 to +90 in 10 degrees per measurement. Here you can jog the positioner. You will see that as I move this, we can move it the elevation, which is also the theta axis, to -45 degrees. The azimuth or phi can also be jogged. With a single click, you can move the position back to 0 degrees. At the top of the software is where you select which type of cut you would like to make, such as an azimuth cut, an elevation cut, or a scan for 3D measurements. The status window shows you how much time is remaining in your measurement, as well as the start, stop, and number of points that is read from the network analyzer. The main portion of the software is the monitor section, where you can watch the measurements live as they are made. The polar plot shows a single frequency, which can be selected from here. This is a live frequency display trace from the VNA. Since our antenna is about a 5 GHz antenna, we will make our monitor frequency 5 GHz. Before we make a measurement, we must calibrate the system. There are a number of ways to calibrate. You can calibrate just the cables, or you can perform a substitution calibration by placing a known reference antenna in place of the antenna under test and calibrating the entire link out. For this measurement, we will do a standard cable calibration. The software supports a scalar cable calibration right from the front page. If we click this button that says Cal System, it will open up the calibration page. To do a standard cable calibration, you will disconnect the cable from your reference antenna and attach it to the positioner, as you will see me do in the video. When the Begin Calibration button is pressed, the software will take a single reading from the VNA. You can see that we have set our VNA to go from 4 GHz to 6 GHz with 51 points. You can save the calibration for use later. When we exit the calibration module, it will ask us if we wish to apply the measurement. Apply the cal to the measurement, and you can see now that it has been applied. Now, the measurement that we make will not have any cable losses. It also calibrates out all of the rotary joints and any other RF components from the setup. I have now reconnected the cable back to the reference antenna and replaced the antenna under test back on the positioner. It's now time to make our measurement. We will do a simple azimuth cut at 5 degrees per measurement. The amplitude plot will show you the dB level of the link over measurement. If this were a substitution calibration, the results you would see here would be an actual dBi. As of now, this is the link, including path loss and the gain of the reference antenna, which we will remove in the next step. You can see that it has about 5 seconds left to complete the measurement. The measurement is now completed. It has captured the data over the entire frequency band at every position. We can now proceed to data processing, where we will see our measurement here. The software provides 4 data storage registers. Here we will place our raw measurement data. We can view our raw data very quickly, and we will see that the signal levels are raw, minus 35 dB. And we can scroll through the frequency range to make sure there's no obvious errors with the measurement. Now we will calculate gain. As mentioned earlier, the path loss is 1 meter. So we will enter in 1 meter, and you will get a nice graph also for your reference to show you what the path loss is at 1 meter over frequency, as well as the dB per inch variation, which means if your measurement's off by 1 inch, then you could possibly be off by 0.22 dB. When we press continue, the button will turn green, showing that we've generated the path loss. We will now import the reference antenna for this reference data for this antenna. The example data happens to be for the exact antenna that we are using. The format of the reference data is very simple. It's frequency in gigahertz with a tab and the gain in dBi. We will press continue. We will now calculate the gain. For this measurement, it's a simple linear gain measurement, so we will calculate linear AUT gain. The gain is now here in our active register as well as register number 4. If we go back to the polar plot, we will now see the numbers are more realistic for a patch antenna. If we move it up to around 5 gigahertz, you will see we are anywhere between 8 and 9 dBi, which is right what this patch antenna should be. At this point, you have a number of options. You can plot it with new plot for a publishable plot, which is very high resolution and vector based. You can also send the data directly to Excel. In Excel, you will have a summary page as well as a sheet with all of the trace data. In this case, it's dBi as well as the phase from the measurement. Phase is included on all measurements that are done with a VNA. In addition to the single frequency polar plots, you can also view over frequency data for any azimuth position. Here is our over frequency data for 0 degrees azimuth. And we can see that this antenna has quite a functional range. While this plot is showing, you can press the Plot with GNU Plot button, and it will plot the over frequency data in the same type of vector-based plot. Pressing Excel Report will send the over frequency data to Excel, just as we did with the polar data. Although we only measured a single azimuth cut of the antenna, there is still 3D data since we measured over frequency. This can be viewed using the ASL frequency 3D plot. This can be viewed in linear or log. We will view it in log dB format. The software has a MATLAB runtime engine built in. Now you can see, because we started at 0 and ended at 360, the main lobe is actually offset. So our plot has an option to offset this by 180 degrees. And if we replot, we will see this is the entire data set that we have measured. A 360 degree azimuth cut over frequency. The plot can be rotated and viewed in any way you wish. This concludes the most basic functions of our software. The other functions, such as spherical 3D and efficiency, require that 3D data will be measured. So we will go back to the main page and make a 3D measurement. If we hit the Reset All Initial Positions button, it will zero the antenna back to 0, and it will clear out the plots in preparation for the next measurement. We will now press the Scan as L button to perform a full spherical measurement. The positioner will rotate to its starting theta position, or elevation, and it will start collecting azimuth or phi cuts around the antenna until it has completed. The estimated time says we have about 12 minutes left to complete this cut. The video will resume when the measurement has completed. Checking back in on the measurement, we will see that it is now just about 2/3 of the way finished, as shown by the progress indicators. You can also note that the system is designed to not rotate the antennas more than 360 degrees. Therefore, if you are measuring something beyond the rated frequency of the rotary joints, you may run cables externally so that for higher frequencies, and it'll rotate to 360 degrees, and then it will unwrap the other direction so that the cables will not get tangled on the system. We will go ahead and pause and let this finish up and check out our 3D data when it is finished. The measurement has now finished its spherical scan. You can see by the progress indicators as well as the status saying the measurement has completed. We will now proceed to data processing again, where we will calculate the gain. For cases where you will be measuring similar antennas with the same reference and same path, you can set up a calibration profile in the front page of the software. This calibration profile will let you specify a reference antenna file and a path distance and perform automatic gain transfer. This way, you do not have to do any post-processing. Your results will be in direct DBI. We can see here that the spherical measurement contains 70,000 data points. That's the number of frequencies, which is 51, multiplied by the azimuth moves and elevation moves. We will go ahead and regenerate our path loss, as well as reload our reference antenna and calculate the gain. Now inside of the polar plot, we now have the elevation slider. So we can view the entire frequency band over the entire azimuth cut over any elevation angle. And if you wish to view an elevation cut, we can click the azimuth slider, which will show the elevation contour for any azimuth position. .3D data can now be viewed for any desired frequency. And here's the spherical pattern for the antenna that we just measured. Many features are available for 3D plots, such as an isotropic sphere at a given dB value, and many other options. Along with 3D spherical data, we can also view efficiency data. By pressing the efficiency button, we can view the efficiency over frequency for the antenna. Also is the radiation resistance and AUT loss. In addition to single cut export data from the polar plot, you can also export the entire data set to either a text file or Excel file. For the Excel export, there's a wide variety of options. For this test, we will go ahead and select a very small range of, let's do 5 gigahertz to 5.2 gigahertz. And we'll go ahead and send this to Excel. And here is our exported data. We have azimuth over elevation, and the magnitude and phase for every frequency in our selected set. This can be imported into your own applications or MATLAB. The 4 data registers can be used also to store other things, such as dual polarization measurements For instance, you would store your horizontal polarization in register 1 and vertical polarization in register 2. These can be used for things such as circular gain measurements using a linear reference antenna, as well as calculating total power factor. That concludes the basic measurement example using the software. Next, I will cover some of the mounting methods for the AUT, as well as how to determine where your phase center is located.
We will now discuss some options for phase centering your antenna. All of our positioners with a phi axis offer the ability to center your antenna in this direction. You can see that in this case, this antenna, ideally, physically, its center is about right here. This particular mount offers about 5 inches of movement. Because this is a patch antenna, its phase center in this direction is relatively small. Therefore, we can mount it directly on the rotary joint, and it's not a large concern. For larger antennas, such as horn antennas or dish antennas, or antennas where the feed points may vary, we recommend that for the phi axis, you make an adjustable bracket so you can position the antenna in this direction wherever the phase center may be. If this horn had a constant phase center from the middle, we would position it about right here. And of course, in this way, it would be positioned about right here. Verifying phase center can be done using your VNA and the memory trace. I will show that to you next. As you can see on the VNA, this is the raw phase information for the entire link. When trying to find the phase center, what you will do is, in this case, we brought up our display screen, and what we've done is we will store this data to memory, and we will divide the data by the memory, and this normalizes the entire phase link. Now, in a non-ideal position, such as here, when I rotate this antenna this way, you will notice on the VNA, you will see how the phase changes over rotation as I move the antenna back and forth. Now in this case, we will slide this antenna back to, which happens to be a known phase center, and we will look at the VNA, and we will rotate the antenna. As you notice, the phase is the change is much less. Now, when I rotate this antenna over those extents, you can see that the change is reduced quite a bit. This phase data over rotation can be read into the software, where we have a module that can actually tell you your minimum phase deviation over rotation. This can help you identify where the true phase center of your antenna is located. Thank you very much for viewing our demonstration video of our antenna measurement system and software. If you have any questions, please let us know.